Good morning. So today, my idea was to discuss some theorems relating about interpolating and sampling sequences for the Pali-Wheeler space. That we saw last time, and Nicola proved that this Pali-Wheeler theorem. Let me make a short recap of what we have seen so far. So we have this Pali-Wheeler space, which now we can see as an entire function, so polymorphism in the complex plane, which cannot grow faster than this exponential, and furthermore, the restriction on the real line is ineligible. And Pali-Wheeler theorem that Nicola proved says exactly that this is exactly Fourier transforms, let's say Fourier transforms of functions in L2 of R, which are supported in A over 2. And we know already from the Pali-Wheeler theorem, sorry, for this from the sampling theorem, that this space has a sequence, namely n over a, which is interpolating and sampling. For example, we saw that in the Hardy space, it's not possible to have. So, particularly in the Hardy space, you don't have any sequences. So the point of this lecture, and tomorrow probably, is to explore some more general interpolating and sampling sequences for the Pali-Wheeler space. And in particular, I want to prove what is called the Berling density theorem, which says that if your sequence is interpolating or is sampling, it has to obey some density conditions for some density defined appropriately, and so on. So let me also remind you some stuff about base theory of abstract Hilbert spaces. In particular, we will require quite a bit more about these systems and frames in abstract Hilbert spaces. So let me remind you that when we talk about interpolation, what we mean is that we have some sequence of points in I will exclusively talk about the Pali-Wheeler space and sequences that lie in the real axis. So let's say you have a sequence xn lying in the real axis, and then you consider the normalized reproducing kernels. So this is the sinc function divided by its norms. It is the norm of A, since xn are real, and then we define in fact interpolation by saying that if Gn is systems. Then this is defined, it is equivalent to say that Xn is interpolated. And if Gn is framed, this is saying that Xn is something. These were our definitions, and what it means to be a Riesz system or frame. It's expressed by some operators. So in particular, we saw that you have this operator T, which goes. Okay, so this is. Let me use H for a general Hilbert space. I mean, implicitly, it's always a polylinear space, but let me say that we have some abstract Hilbert space things. We have this operator which sends sequences to different combinations, and then a Riesz system is equivalent to say that T is bounded above and below. This was practically our definition, because what we said was that this system means that we have an inequality of this type. In particular, this is equivalent to say that this operator is bounded above and below, and the framing by definition means that another operator, which happens to be the adjoint of this, which then function F, it's the sequence of expectations. Frame means exactly that this F is bounded below and below. So these are all definitions pretty much introduced. And okay. So the point is to yes. What did I want to say? Yes. So I want to go a little bit deeper on this theory of Riesz systems and frames in the abstract setting, which is going to be useful to apply to this problem of interpreting some sequences in the polylinear space. So in particular, yes. So we keep the notation H for the abstract Hilbert space, but then our application will be to the polylinear space. And I want to talk about what is called a dual Riesz system. So a dual Riesz system is the following thing. So let's suppose that Gn Riesz system then I can find another risk system. Let's call it Fn. Is with the following properties. So, first of all, it's bi-orthogonal to Gn. So this means that Fn Gn is delta Nn. Secondly, they span exactly the same space. So they span N is equal to the span Vn. So there exists exactly a unique risk system with these two properties. So there exists even here. That is 1 and 2. And furthermore, when you have this dual risk system, then it's useful because of the following reason, because you can represent arbitrary vectors in the Hilbert space in the following way.
Yes.
Yes. Okay. Yes, so maybe I can go a bit slower. The point is that if I have this dual risk system, then for a vector in A, I can represent this in this way. This convergence in one. So of course, if you have an orthonormal basis, which is a complete risk system, then its dual risk system is exactly itself. And you can see it also from the representation, because in our basis, the representation here you have Gn coefficients with respect to Gn. If you have a general risk system, then you need this representation. Sorry, to be this is not correct. This might not be complete. This system might span a smaller space than a small filter space. So this is not, it does not reproduce ends. It reproduces with the projection on the space spanned by the Gn. Okay. If it's completely system or a risk basis, then of course this projection identity reproduces the function itself. So the proof is easy. So what you do is so suppose first of all take it, let's call V. Let's consider this state that all this Gn is fine. So if this is not the whole Hilbert space, then we can just restrict on the space that they span and work there. So it's equivalent and work there. So we can assume without loss of generality that they span the whole space that it is a risk basis. Otherwise, we just restrict on the space they span. Okay. But this means that this operator T goes from L2 to H So this operator will send an to this linear spans. So it's bounded above and below because we suppose that we have a risk system, but this means that it has a dense range, but since it's bounded above and below, its range is closed, so it's adaptive. Okay. So in fact, it is a Hilbert space isomorphism. And then to find your new risk system, you just consider t minus 1 of the, and you call them that. Okay. So why this makes sense? Because okay, t minus 1 is well defined because it is a Hilbert space isomorphism, and it maps H to L2. And then when I take star, it maps, no, sorry, of EN. So t minus 1 star goes from L2 again to H. So I take the standard orthonormal basis here, which are the vectors here. And I call them that. And I claim that this is the dual risk basis to the GM. So EN is the standard orthonormal basis. So why is that? Why is that? Let me erase. So let's first show the bidual biorthogonal relation. So if I consider now F and G and M, and this by definition is T minus 1 star of E N. There is GM, and this is the linear product in H. But if I apply the star on the other part, it's T minus 1 GM in L2. But which vector is mapped to GM under T is of course the mth vector of the standard orthonormal basis. So this is exactly delta n. So we have this biorthogonality relation between the two vectors. Then, as a system, so Fn as a system has associated some operator, let's say R, which goes from L2 to H. So it is the operator associated to the system, and T is the operator associated to the system Gn, which sends, I don't know, some sequence to this. But what is this operator? Fn is defined in this way. So this is the T minus 1 star E and En. So which is T minus 1 star applied to the sequence Vn. So this operator is exactly T-1 star. And since this operator is a Hilbert space isomorphism, by definition, Fn is a Riesz system, a Riesz-based one, okay? Because it's when I apply -1 star to T, which is a Hilbert space isomorphism, I get a Hilbert space isomorphism, which proves that Fn is a Riesz system, a Riesz-based system with our assumption. So in particular, it spans the whole space. So the span of Fn is equal to the span of the Gn. And then to see this last relation, you can work as follows. We work without loss of generality in the case where the span of the Gn is a whole Hilbert space. So in this case, we want to prove that H is equal to this thing. We want to prove this. So let's check what this vector. Let's check what this vector gives us if we pair it with some of the vectors Fn. Now this thing it converges in norm because Gn is a Riesz system. So I can just take out the sum. And G. It's by construction, by the orthogonality relation, this gives me just the Vm is a term here. So this vector, let's call it U, paired with Fn is equal to H paired with Fn for all n. Okay. But Fn span a dense subspace, span a dense space, span a dense set of the space. So in particular, this means that this H must be equal to U. So we have this. So this is the story about this case. It's a useful tool. It gives you a way to represent arbitrary elements in the Hilbert space, and we will see how we want to implement this idea. So now, the idea is probably to do just the interpolation part today and the sampling part tomorrow. So I will skip the analogous part for frames, which is a bit more not so straightforward. I think this explaining the idea of how interpolation works is much more transparent. Anyhow, so going back to the Pali-Wiener space. So what is our goal? We haven't talked exactly about what we want to prove. It is this theorem by Berlin. So if you notice the integer, of course they are very regular. Okay, they occur the sequence n over 8. It occurs every 1 over 8. Of course, it occurs in every interval of length 1 over 8. So what Berling noticed was that this is not a coincidence. So this you can define some density of the points in the real line with for the integers for the sequence n over 8. Of course, it's going to be exactly 8, and which has to obey certain inequalities if your sequence is interpolating or if it's sampling. So the exact density that defined is defined as follows. So suppose you have some sequence of points. Say the I real points. Okay. Without loss of clarity, let's assume that they are separated by some constant delta. Okay. I mean, you can show that this is going to follow, but let it assume it. It's a reasonable thing to assume for the moment. Then, so we could Berling define the following quantities. So we have two densities, upper Berling density which is defined as follows. So what do you do is you look at all, you fix a length of an interval, okay? And then you look at the maximum number of points that you can have in an interval of fixed length. So you have an interval of length, let's say R, and you look at the maximum number of points that you have in such an interval of the sequence. Okay? Then you normalize by the length of the interval, and then you take the limit. When the length of the interval goes different. Okay, this is the upper Berling density. We're going to prove this limit exists. And then the lower density. So it is defined analogously. You just take the minimum number of points that you can find in some interval of fixed length. So you take the mean. And you take the length. This is the lower Berling density. And the remarkable result is that if your sequence is interpolating for the Palladino space, then the upper Berling density is bounded by A, exactly, as it is to be expected. And if it is sampling, then the lower Berling density is bounded below by A again. So theory. So Berling, then I want to mention also Catane and Landau. Because they worked on, they generalized this theory in some Palladino spaces where the spectrum might not be supported in an interval minus A by 2A2, but in a more complicated set. And so they want to complete in this theory. And this is the necessity part, let's say. So, as I said, so if lambda is interpolating, then which is less than A, if the lambda is 1. So, yes, some comments. Of course, this implies that if you have a sequence which is interpolating n sampling, such as the sequence n over A, then the density, the upper and the lower value densities have to coincide and be equal to A. So this is a critical density as it is usually called. In fact, this sequence is a prototypical sequence of density A. So let me ask this as a corollary. So if lambda is equal to A. So what this means, it means that in whichever way I take a sequence of intervals, so this is equivalent to say that for every sequence of intervals with length going to infinity, then the number of points of lambda in the interval IN is asymptotically this ratio is asymptotically A. Okay. So it's a strong density condition in the sense that it does not really matter where I center these intervals. They can be an arbitrary sequence centered anywhere, which that has increasingly large length. And this density condition. So another remark is that
the only if part is not straightforward.
the only if this direction.
No.
It's,
I mean, if you have the density condition, then you understand.
I mean the theory, not in this corollary.
Not the corollary.
No, so what I'm saying is that this is the equivalent, not the sum.
Oh, okay.
Yeah. No, it doesn't follow, and it's not true. That's what I was going to talk about. So in fact, so what is the situation after the theory? You don't have the reverse implication. Okay? It is another big theorem, again by Berling in the same work, that says that if you have strict inequality here, then the sequence is interpolating, and if you have strict inequality there, the sequence is summed. So then the final question is to understand what happens for sequences which have density exactly equal to A. So which of them are sampling or interpolating or both? And this is a quite big question. I mean, answered recently, many years after Berling's work. The point in presenting, I mean, apart from the fact that presenting the only if part, so the strict inequality here implies that the corresponding here. I'm not going to cover this, but the point is that in the necessity part, I think we were going to see again this abstract Hilbert space tools being used really heavily, and the actual hard analysis part is going to be minimal. And it is a technique that is very readily generalized to other settings. So I think it's useful also as a technique to see. Now, so there are a few things remaining before proving the theorem. One of them is to prove that this limit actually exists. So let me do that before I start proving it. The proof is not extremely exciting, but I think it's quite typical of how you prove existence of this density in all other similar situations. So maybe it's instructive. So let me define. I will do the upper density, the lower in the analogies. We'll define f of r to be this ratio. So this is actually a maximum, okay? Because of the separation condition, you cannot have arbitrary remaining points in an interval of fixed length because all these points are delta separated. And since this quantity here only takes natural number integer values, the maximum has to be achieved somewhere at some point. Then we can argue as follows. So take some R1 less than R2 and consider an interval of length R2. An interval I. Okay. So here I have some arbitrary interval. And suppose that this is maximum, this the number of points in this interval is some n2. Okay. So f of R2 is that n2 divided by R is smaller than R2 divided by n2. The point is to relate with the value of the function at R1. How I do this? I can cover this interval by other smaller intervals of length R1. Okay, so I can put adjacent intervals, each of length R1, which cover the interval edges. how many of them I need? I need at most R2 divided by R1 into the part plus 1. But then on each of these intervals, right, I can have at most this max where here at R1 point. So let's say N1 max. Okay, by definition of this quantity, of course. Okay. So in total, in I2, I cannot have more than N1 times the number of interval points. Okay. So N2 cannot be really bigger than the number of the intervals that I use to cover times, so the number of points in its interval times the number of the intervals. It's smaller than N1 times R2 divided by N. So this I2 it was arbitrary, so I might even choose it to be the one that realizes the maximum. So rearranging, so I divide by R2 over R1, so I get N2 divided by R2 is less or equal than N1 divided by R1 times so I divided by R2 and then here I have yes. Which this is by definition f of R2 and this is f of R1. And this holds for all R2 greater than R1. Here I take a unit soup as R2 goes to infinity. And of course, this term now is negative 1. And this holds for all R1 now, so I just take the limit here. And I have that the limit soup for f R goes to infinity is less or equal than the limit in. Which means that the limit exists. I think this is when you define densities of sequences given other kind of densities. This kind of arguments are very typical to prove the existence. And the lower Bernoulli density is very similar to show that it exists.
Sorry, Nikos, what have you written? Lim sup of F is less or equal of what?
Lim,
Minf.
yeah, but
Okay,
yes,
thank you. Thanks.
Okay, so this was since I let R2 go to infinity, then this now falls for all R1. So I can also take a limit as R1 goes to infinity. Okay, I will make a break and then I'll continue during the second part. So as I was saying, this proof it uses minimally the structure of the Pali-Wiener space itself. It's mainly based on Hilbert space considerations. So in fact, it's readily generalizable, and it is a very recent proof. I don't remember when Berlin proved the density theorem, but this proof it's by Orlewski and Nixon, and it's put in 2012. So it starts where we place with this length. So suppose that yes, suppose. So now we are in the Pali-Wiener space. So Fn and Gn are individual. There is thickness in the Pali-Wiener space. Then we have this. We can actually say that this expression, so which is evaluated for every x in R, is positive and is less than A. And the convergence is absolute and uniform. Okay. This is so if you think of the space as a producing current Hilbert space, is quite straightforward because okay. So what is Fn calculated at x is the scalar product of Fn with the current. And Gn of x bar is the Ax at A with Gn. So instead of putting a bar, I just flip the order in the scalar product. But then I can take the sum inside. So what do I do? I want to. So which sum I want to take inside? I will take this sum inside the second part of the inner product. So this is going to be equal to K X A sum over all n, and then here I will have f n k x a bar, because it's skew symmetric. Let's say times gn. And the point is that we saw that this is, since Fn is the dual race system of Gn, then this expression is exactly the projection of this function on the space generated by expanded by Gn. Okay. This is the property that we saw. So this is the projection on the space bound by Gn of the vector k x a. But this is exactly, I can put a projection here for free. So this is exactly the norm of this projection. But projections are contracted, so this is less than equal than the norm of kx squared with k. Incidentally, we also proved that this is positive because it's equal to a norm vector. So if you are worried about changing the convergence or explanation, you can prove that this in fact converges and so on, but we are only going to apply it for finite remaining vectors. So in practice, there are no problems of convergence. But you can actually prove that it has convergence on its endpoint events. So that's the lemma. And now you can pass to the actual proof. So with proof, I mean the first part. Also, again, here the only thing that we use from the Pauli-Wiener space is that this norm is equal to A. Okay. Only this feature is particular to the Pauli-Wiener space. Everything else holds generally. Okay. So. Well, now let lambda to be our sequence of the points lambda n, and then Gn is the normalized kernel vector. Here. But in the Pauli-Wiener space, these are all translations of one function. Okay, so this is that I can write it. So the norm is square root of A, and the kernel is defined explicitly is A times string in A. It's A, and here I just I denote by G without an index that's distinct function, so everything is I love the context. So the point is that this Gn are translations of the string. Okay, so where G is for what it has to be square root of A string. So now let's MC positive. And this is, of course, in L2 of R, so we can find some E epsilon. The tail of the L2 norm of this thing is smaller than epsilon. So when I integrate this G of X, this is smaller than epsilon. Okay. This is clear. And then the clever idea is to consider from all this. So I fix an interval. Okay, I fix an interval. I want to have an estimate for this density, so I have to count somehow the points in this interval. The idea is to consider this subspace of the polylinear space spanned only by Gn for lambda n in this interval, so fixed. And then I consider this finite dimensional space, in fact, is the span of the G such that n such that lambda n will be infinite. And Pi is the equivalent on VI. Okay. So my RIS system has some bioorthogonal system, some global bioorthogonal system. So let's also that the U1 system attention here, it does not follow that if I consider the fn's for n such that lambda n is in I, then this subset is the dual RIS system of this for the Gn only for this lambda n is such that lambda n is in I. What is true, and the claim is true, and they will prove, is that the dual of this restricted one, so of Gn for n such that lambda n is in I, is
any numbers you vanish, right? On
Fn,
all the lambda n for n.
yeah,
It's like an entire function.
yeah. Fn must vanish. Yeah, it's because they are orthogonal to the reproducing terms. This means exactly that they vanish on the other points.
So it's making it impossible to write them down explicitly.
Yes.
And
Yeah. It's. I mean, it's a discussion that we had every function in the polylinear space. You can write it. It's genus one, so you can write it explicitly if you know the zeros.
yeah, actually, I mean,
Yeah. Yeah, you can write them quite explicitly, but we will see that we will not require anything about their behavior as holomorphic functions. So the RIS system of this restricted one is the projection on the space that is generated of the fn's. So why I'm saying this? Because our definition of the dual RIS system was that they have the bioorthogonality relation with Gn and Fn, of course, they have even restricted, but they also respond the same state. So the problem is that if you consider some subset of the Gns, then the corresponding subset with the fx might span different space, so it might not be might not satisfy the second requirement for definition. So to prove that this is the dual array system of that, we have to prove that they are orthogonal still. Which is quite straightforward, because if I take n subset of lambda and this unary, and g times the projection n, since gn is already in the space where this operator projects, okay, so they still satisfy the bi-orthogonal relation. And now, obviously, this belongs to the span B by definition, because we project on VI. And I claim that they span the whole space because you cannot have anything. So because if you have some linear combination of this, which is orthogonal to all the GNs. So if this is not the case, I can find some linear combination of this function. Remember that all these things are finite sums, okay? So not which is orthogonal to all Gn. If this is not the case, but of course, by orthogonality, this is exactly an yes. Okay. So this must be the zero vector. So in fact, they span the whole VI, and they are by orthogonal to Gn. So it is by definition the dual array system of this finite array system. Why all this mess? Just to say that we can apply the previous lemma. So what I want to keep this claim. What does the previous lemma say? It says take any array system and it's dual, and you have this relation. Thus, this term is a positive quantity. G and X. And this objection will be on smaller than A. Good. And now I integrate this thing not over I, but over I, which is a bit fattened by a factor of b in its end. So I is some interval here, standard at some point, and it has some length r. I just take the concentric interval with where I add b on both sides. Okay, so this is in total the interval of length r plus 2b, and I call it RB index b. By flattening this interval, and I integrate this function over this flattened interval IB. And an integral of IB Gn x e I e. And here I get, it's a constant, so I get a times the length of the interval IB, which is r plus 2 times b. And the point is, what is this quantity here? So it is of course we cannot know with that, we can estimate it. First of all, I take advantage of the fact that I know what is the inner product of Gn with pi at n on the whole of r. So I write integral on the whole of r minus an integral on the pi. Because I know that this is one, and it was my assumption that it is here. It is by orthogonal to that, so the inner product should be one. Then I have the rest. Sorry, this is r minus. I have the rest, which I will have to estimate. So the estimate is really not that deep, just pushes values inequality. So remember that Gn of x is just a translation of some constant function. I apply push path. Also, the second part. Okay. And so this is that I just say, okay, just integrate over fold realign, you will get something bigger. So let me, yeah, I estimate these things separately. Which is smaller than the integral of the this function over the whole real line, which is the norm of this projection. Which is smaller than projection subtractive, it's smaller than the norm of the Fn. But Fn form a Riesz system, so they have, in particular, by applying the upper estimate in the Riesz system condition, this is bounded by some constant, absolute constant B. While for this part, remember how B was chosen. So for this part, yes. So if what I'm claiming is that this other integral is just smaller than the integral of this b of x or x greater than b. When integrate. Okay, so it should be quite clear, but it's just that because this is a smaller domain than that. Okay, because if yeah, so when I'm integrating here, I'm saying that the x has a distance to the center of the integral to the interval bigger than r plus b. Okay, this is the definition of the interval id. But then, if this happens, the modulus of x is bigger than sorry, x minus lambda n is bigger than that, which means that the modulus of x is bigger than x minus lambda n. Okay. But this is bigger than r plus b, and this is at most r by how this lambda and r solved. Okay. So this is the okay, and this the way that b was solved, so it was that so that this is more than epsilon squared. So all in all, this is smaller than a constant, absolute constant, times x. Which means that, yes.
Sorry, why the last inequality is true?
This one?
No, the in the left.
Here.
Yeah, I don't get the because
So
this.
when we're integrating here, it means that x minus lambda n, it's the distance to the center of the interval is bigger than r plus b. Because
Okay.
so here is triangle inequality.
But r is the length of the interval.
R is the length of I, and
so why?
Okay, so the R was the length. You mean not the radius, it's the length.
No, sorry, I didn't.
No, I see what you mean.
So I noticed the center. What?
I know the center. Yeah, sorry. So R was the length. Okay, so I have to put R on the two here. This is what now it's correct probably.
And I don't get also the triangular inequality. Seems that the signs are not.
Yes.
When you do a picture, it's here.
If you do pictures, it's clear. Link pictures on black.
From X,
Sorry, but
you have to put it down. This,
Yes.
this.
Pictures are clear when you are when you are not on the black.
I mean, now you do your original picture.
Yes. So
yeah, of course, maybe it's just to fix the
yes.
And
inequalities back.
X side and X is outside, you have to jump that.
Yes. Yes. You have to jump at least B with yes, which means that
The next thing is outside of the big thing. And your angle is inside of this whole thing. And you have to jump that.
yes.
No matter what is the
Yeah,
angle,
yeah.
the quality is.
So yes. Yeah, so it seems yes, this is the original interval I. This is the pattern interval IB. And since lambda n is inside and x is outside the big one, as Nicola said, the difference has to be at least this gap, and this gap is big. Yeah. You can prove it also with the triangular inequality.
With.
But not
This looks like more like a video game.
Great. Yes. So what we proved, let me write it here to keep it, is that this is bigger than 1 minus some constant times x. Okay, that's what comes up with this reasoning. And we have the integrating this relation to the lemma that this more than A times R plus 2B. Okay, but this is also yes, this is so this was in fact not this what we want to keep is that so this is that integrating with the rest. is smaller than that. Okay. So as we said, this is 1 minus this integral. But when I do 1 minus that integral, I get to some ones as many as the number of lambda in this interval times. So I have the number of points in I minus the sum again of the rest. But this is bigger than, like now putting absolute values inside. So now I get the upper estimate from that, which becomes a lower estimate with the minus. Again, each one of these terms is smaller than a constant times epsilon. And then I get, again, that many ones. Okay. So, all in all, we proved that the number of points in time times 1 minus a constant times epsilon is smaller than 8 times alpha 2d. So now I divide by r. And I take the limit as I take the maximum first over all area. Then r. Then I take the limit as r goes to infinity, and I have on the left the upper Bernoulli density smaller than 8. But epsilon was arbitrary. Now b does not appear with depending on epsilon. So this implies that the Bernoulli density is not. This is the and this is the first part of the theorem. Yeah, I think I will stop here because the sampling part is a bit more involved, and it's better if we start it tomorrow.
So you use nothing.
Nothing.
I mean, you use that effectively.
We have the translation.
Yeah, translation. Which basically says that. Yeah, even the reduced colors. I mean, they're generated geometrically by one part.
Yes.
Which is something.
Yeah, in fact. Yeah, it's I think it's a very nice proof. Also, in
the different space, one space, since one can say something about sentence sequences, which are not real.
yes, you can. It's different if you consider sequences in the strip, in a strip, or sequences which may be outside.
As long as you have a control of the norm of G on horizontal.
Yeah,
Makes sense.
Yeah, tomorrow, I want to do the sampling or frame part. It's used, I think, a bit more of the structure of the space, but only some things will indicate the factors in the realignment of the pavilion space, and that's it. Of course, we have not even proved that there exists some sequence which is interpolating and it's not the integers, but this is an interesting topic by itself. I mean, for example, one other topic which I decided in the end to leave out was this theory by Cadets, which says that if you take the sequence lambda n, which is just the perturbation of, so take A to be equal to 1. And then if lambda n is just the perturbation by at most 1/4 minus epsilon. Then the sequence lambda is sampling and interpolating. So so in fact, sampling and interpolating sequences are very stable. Integers are very stable under perturbations in the polynomial space. But so that you can, in fact, there are many. Even
They follow in these visuals.
they follow that, yeah, of course, they have to follow, they have to have exactly that Berlin density. Yeah.
Sorry, Nikos, tomorrow in which room is your lesson?
It's downstairs in Enriquez. Enriquez.
Enriquez,
Ground floor, yes.
ground floor math department.
Yes.
Thanks.